All right, so let's get started. So thank you all for coming to day 2 of 6S191. We're really excited to have you for these 2 lectures and lab today, which are largely going to be focused on deep learning for computer vision. So to motivate, I think we can all agree that vision is one of the most important human senses, and sighted people rely on vision quite a lot for everything from navigating in the physical world to recognizing and manipulating objects to interpreting facial expressions and understanding emotion. And I think it's safe to say that for all of us, or many of us, vision is a huge part of our lives. And that's largely thanks to the power of evolution. Evolutionary biologists trace the origins of vision back 540 million years ago to the Cambrian explosion. And the reason that vision seems so easy for us as humans is because we have 540 million years of data that evolution has effectively trained on. And if you compare that to other capabilities like bipedal movement and language, the difference is quite significant. And starting in the 1960s, there was a surge of interest in both the neural basis of vision and how to systematically characterize visual processing. And this led to computer scientists beginning to wonder about how findings in neuroscience could be applied to achieve artificial computer vision. And it all started with these series of seminal experiments from 2 neuroscientists, David Hubel and Torsten Wiesel, who were working at Harvard at the time. And they were looking at processing in the visual cortex of cats. And what they were able to demonstrate was that there are neural mechanisms for spatially invariant pattern recognition, and that certain neurons in the visual cortex respond very specifically to specific patterns and regions of visual stimuli. And furthermore, that there's an exquisite hierarchy of neural layers that exists within the visual cortex. And these concepts have transformed both neuroscience and artificial intelligence alike. And today, we're going to learn about how to use deep learning to build powerful computer vision systems that have been shown to be capable of extraordinarily complex computer vision tasks. So now that we've gotten a sense at a very high level of why this is important and sort of how our brains may process visual information, we can turn our attention to what computers see. How does a computer process an image? So, well, to a computer, images are just numbers. So suppose we have this picture of Abraham Lincoln. It's made up of pixels. And since this is a grayscale image, each of these pixels is just a single number. And we can represent this image as a 2D matrix of numbers, one for each pixel in the image. And this is how a computer sees this image. Likewise, if we were to have an RGB color image, not grayscale, we can represent that with a 3D array, where now we have 2D matrices for each of the channels R, G, and B. So now that we have a way to represent images to computers, we can think about what types of computer vision tasks we can perform. And 2 very common types of tasks in machine learning broadly are those of regression and those of classification. In regression, our output takes a continuous value, while in classification, our output takes a single class label. So, for example, let's consider the task of image classification. Say we want to predict a single label for some image. And let's say we have a bunch of images of US presidents, and we want to build a classification pipeline to tell us which president is in an image, outputting the probability that that image is of a particular president. And so you can imagine, right, that in order to correctly classify these images, our pipeline needs to be able to tell what is unique about a picture of Lincoln versus a picture of Washington versus a picture of Obama. And another way to think about this problem at a high level is in terms of the features that are characteristic of a particular class. And classification can then be thought of as involving detection of the features in a given image and sort of deciding, okay, well, if the features for a particular class are present in an image, we can then predict that that image is of that class with a higher probability. And so if we're building an image classification pipeline, our model needs to know what those features are, and it needs to be able to detect those features in an image in order to generate this prediction. One way to solve this problem is to leverage our knowledge about a particular field, say those of human faces, and use our prior knowledge to define those features ourselves. And so a classification pipeline would then try to detect these manually defined features in images and use the results of some sort of detection algorithm to do the classification. But there's a big problem with this approach. And if you remember, images are just 3D arrays of effectively brightness values. And they can have lots and lots and lots of variation, such as occlusion, variations in illumination, and intra-class variation. And if we want to build a robust pipeline for doing this classification task, our model has to be invariant to these variations while still being sensitive to the differences that define the individual classes. Even though our pipeline could use these features that we, the human, define, where this manual extraction will break down is actually in the detection task. And that's, again, due to the incredible variability in visual data. Because of this, the detection of these features is actually really difficult in practice, because your detection algorithm would need to withstand each of these different variations. So how can we do better? We want a way to both extract features and detect their presence in images automatically in a hierarchical fashion. And again, right, you came to a class on deep learning. We hypothesized, right, that we could use a neural network-based approach to learn visual features directly from data without any, manual definition, and to learn a hierarchy of these features to construct a representation of the image that's internal to the network. For example, if we wanted to be able to classify images of faces, maybe we could learn how to detect low-level features like edges and dark spots, mid-level features like eyes, ears, and noses, and then high-level features that actually resemble facial structure. And we'll see how neural networks will allow us to directly learn these visual features from visual data if we construct them cleverly. Going back in lecture 1, right, we learned about fully connected architectures where you can have multiple hidden layers and where each neuron in a given layer is connected to every single neuron in the subsequent layer. And let's say that we wanted to use a fully connected neural network for image classification. In this case, our 2D input image is transformed into a vector of pixel values. And this vector is then fed into the network where each neuron in the first hidden layer is connected to all neurons in the input layer. And here, hopefully, you can appreciate that by squashing our 2D matrix into this 1D vector and defining these fully connected connections, all spatial information is completely lost. Furthermore, in defining the network in this way, we end up having many, many different parameters, right? You need a different weight parameter for every single neural connection in your network because it's fully connected. And this means that training a network like this on a task like image classification becomes infeasible in practice. Importantly, right, visual data has this really rich spatial structure. How can we leverage this to inform the architecture of the network that we design? To do this, let's represent our 2D input image as an array of pixel values, like I mentioned before. And one way we can immediately use the spatial structure that's inherent to this input is to connect patches of the input to neurons in the hidden layer. Another way of thinking about this is that each neuron in a hidden layer only sees a particular region of what the input to that layer is. And this not only reduces the number of weights in our model, but also allows us to leverage the fact that in an image, pixels that are spatially close to each other are probably somehow related. And so I'd like you to really notice how the only region only a region of the input layer influences this particular neuron. And we can define connections across the whole input by applying the same principle of connecting patches in the input layer to neurons in the subsequent layer. And we do this by actually sliding the patch window across the input image. In this case, we're sliding it by 2 units. And in doing this, we take into account the spatial structure that's inherent to the input. But remember, right, that our ultimate task is to learn visual features. And the way we achieve this is by weighting these connections between the patch and the neuron in the next layer so as to detect particular features. So this principle is called, what you can think of it as is applying a filter, essentially a set of weights to extract some sort of local features that are present in your input image. And we can apply multiple different filters to extract different types of features. And furthermore, we can spatially share the parameters of each of these filters across the input, so that features that matter in one part of the image will still matter elsewhere in the image. In practice, this amounts to this patchy operation that's called convolution. And if we first think about this at a high level, suppose we have a 4x4 filter, which means we have 16 different weights, right? And we're going to apply this same filter to 4x4 patches in the input and use the result of that filter operation to define the state of the neuron that the patch is connected to, right? Then we're going to shift our filter over by a certain width, like 2 pixels, grab the next patch, and apply that filtering operation again. And this is how we can start to think about convolution at a really high level. But you're probably wondering, how does this actually work? What am I talking about when I keep saying, oh, features, extract visual features? How does this convolution operation allow us to do this? So let's make this concrete by walking through a couple of examples. Suppose we want to classify x's from a set of black and white images of letters, where black is equal to -1 and white is represented by a value of 1. To classify, it's really not possible to simply compare the 2 matrices to see if they're equal, because we want to be able to classify an x as an x, even if it's transformed, rotated, reflected, deformed, etc. Instead, we want our model to compare the images of an x piece by piece, and those important pieces that it learns to look for are the features. And if our model can get rough feature matches in roughly the same positions, relatively speaking, in 2 different images, it can get a lot better sense at seeing the similarity between different examples of x's. So each feature is like a mini image, right? A small 2-dimensional array of values. And we can use these filters to pick up on the features that are common to x's. So in the case of x's, right, filters that can pick up on diagonal lines and a crossing capture what's important about an x. So we can probably capture these features in the arms and center of any image of an x. And I'd like you to notice that these smaller matrices are the filters of weights that we'll actually use to detect the corresponding features in the input image. Now, all that's left is to define an operation that picks up where these features pop up in our image. And that operation is convolution. And convolution is able to preserve the spatial relationship between pixels by learning image features in small squares of the input. And to do this, what we do is we simply perform an element-wise multiplication between the filter weight matrix and the patch of the input image of the same dimensions. And this results, in this case, in a 3x3 matrix. And here in this example, all the entries in this matrix are 1. And that's because everything is black and white, either -1 and 1. And this indicates that there is a perfect correspondence between our filter matrix and the patch of the input image where we multiplied it, right? So this is our filter, this is our patch. They directly correspond, and the result is as follows. Finally, if we add all the elements of this matrix, this is the result of convolving this 3x3 filter with that particular region of the input, and we get back the number 9. So let's consider another example, right, to hopefully drive this home even further. Suppose we want to compute the convolution of this 5x5 representation of an image and this 3x3 filter. To do this, we need to cover the entirety of the input image by sliding this filter over the image, performing this element-wise multiplication at each step, and adding the outputs that result after each element-wise multiplication. So let's see what this looks like. First, we start off in this upper left corner. We multiply this filter by the values of our input image and add the result, and we end up with the value of 4. This results in the first entry in our output matrix, which we can call the feature map. We next slide the 3x3 filter over by 1 to grab the next patch and repeat this element-wise multiplication and addition. This gives us our second entry, 3. We continue this process until we have covered the entirety of this input image, progressively sliding our filter to cover it, doing this element-wise multiplication patch by patch, adding the result, and filling out our feature map. And that's it. That's convolution. And this feature map, right, this is a toy example, but in practice, you can imagine that this feature map reflects where in the input image was activated by this filter, where in the input image that filter picked up on, right? Because higher values are going to represent like sort of a greater activation, if you will. And so this is really the bare bones mechanism of this convolution operation. And to consider really how powerful this is, different weight filters can be used to produce distinct feature maps. So this is a very famous picture of this woman who's called Lena. And as you can see here, in these 3 examples, we've taken 3 different filters, applied this filter to the same input image, and generated 3 very different outputs. And as you can see, by simply changing the weights of the filters, we can detect and extract different features like edges that are present in the input image. This is really, really powerful. So hopefully you can now appreciate how convolution allows us to capitalize on the spatial structure that's inherent in visual data and use these sets of weights to extract local features. And we can very easily detect different features simply by applying different filters. And these concepts of preserving spatial structure and local feature extraction using these convolutions are at the core of the neural networks used for computer vision tasks, which are called convolutional neural networks, or CNNs. So sort of with these bare bones mechanism under our belt, we can think about how we can utilize this to build neural networks for computer vision tasks. So let's first consider a CNN designed for image classification. Remember, the goal here is to learn features directly from the image data. This means learning the weights of those filters and using these learned feature maps for classification of these images. Now, there are 3 main operations to a CNN. The first is convolution, which we went through, right? And we saw how we can apply these filters to generate feature maps. The second is applying non-linearity, the same concept from lecture 1. And the third key idea is pooling, which is effectively like a downsampling operation to reduce the size of a map. And finally, the computation of the class scores and actually outputting a prediction for the class of an image is achieved by a fully connected layer at the end of our network. And so in training, we train our model on a set of images, and we actually learn those weights of the filters that are going to be used in the network, as well as the weights in the fully connected layer. And we'll go through each of these to break down this basic architecture of a CNN. So first, right, as we've already seen, let's consider the convolution operation. As before, each neuron in a hidden layer will compute a weighted sum of its inputs, apply a bias, and activate with a non-linearity. That's the same exact concept from lecture 1. But what's special here is this local connectivity, the fact that each neuron in a hidden layer is only seeing a patch of what comes before it. And so this relation defines how neurons in convolutional layers are connected. What it boils down to is the same idea of applying a window of weights, computing a linear combination of those weights against the input, and then activating with a nonlinear activation function after applying a bias. Another thing we can think about is the fact that within a single convolutional layer, we can actually have many different filters that we are learning, different sets of weights, to be able to extract different features. And so the output layer, after a convolution operation, will have a volume where the height and the width are the spatial dimensions dependent on the input layer. So if we had, say, a 40 by 40 input image, the width and height would be 40 by 40, assuming that the dimensionality scales after the operation. And these dimensions are dependent on the size of the filter as well as the degree to which we're sliding it over the input layer. Finally, the depth is defined by the number of different filters that we are using. The last key thing that I would like for you to keep in mind is this notion of the receptive field, which is essentially a term to describe the fact that locations in input layers and are connected to, a neuron in a downstream layer is only connected to a particular location in its respective input layer, and that is termed its receptive field. Okay, so this kind of, at a high level, explains sort of how these convolutional operations work within convolutional layers. The next step that I mentioned is applying a nonlinearity to the output of a convolutional layer. And exactly the same concept as the first lecture, we do this because image data is highly nonlinear, right? And in CNNs, it's very common practice to apply nonlinearities after every convolution operation. That is, after each convolutional layer. And the most common activation function that is used is called the ReLU function, which is essentially a pixel-by-pixel operation that replaces all negative values that follow from a convolution with a 0. And you can think of this as sort of a thresholding, where negative values after convolution indicate sort of negative direction of a negative detection of that associated feature. The final key operation in CNNs is pooling. And pooling is an operation that's used to reduce dimensionality and to preserve spatial invariance. And a common technique is called max pooling. And it's shown in this example. And it's exactly what it sounds. You simply take the maximum value in a patch, in this case, a 2x2 patch, that is being applied with a stride of 2 over this array. And the key idea here is that we're reducing the dimensionality going from one layer to the next. And I encourage you to think about other ways in which we can perform this sort of downsampling operation. So these are the 3 key operations to CNNs. And we're now ready to put them together to actually construct our network. And with CNNs, the key is that we can layer these operations hierarchically. And by layering them in this way, our network can be trained to learn a hierarchy of features present in the image data. So a CNN for image classification can be broken down into two parts. First, this feature learning pipeline, where we learn features in our input images through convolution, through these convolutional layers. And finally, the second half is that these convolutional and pooling layers will output high-level features that are present in the input images. And we can then pass these features on to fully connected layers to actually do the classification task. And these fully connected layers can effectively output a probability distribution for the image's membership over a set of possible classes. And a common way that this is achieved is using this function called a softmax, whose output represents a categorical probability distribution over the set of classes that you're interested in. OK, so the final key piece, right, is how do we train this? And it's the same idea as we introduced in lecture 1, backpropagation. The important thing to keep in mind is what it is we're learning when we're training CNNs. What we learn when we train a CNN model is the weights of those convolution filters. At another degree of abstraction, right, you can think of this as what features the network is learning to detect. In addition, we also learn the weights for the fully connected layers if we're performing a classification task. And since our output in this case is going to be a probability distribution, we can use that cross-entropy loss that was introduced in lecture 1 to optimize via backpropagation. So arguably the most famous example of CNNs, and for CNNs for classification, and maybe CNNs in general, is those trained and tested on the famous ImageNet dataset. And ImageNet is a massive dataset with over 14 million images across over 20,000 different categories. And this was created and curated by a lab at Stanford, and is really become a very widely used dataset across machine learning. So just to take an example, in ImageNet, there are 1,409 different pictures of bananas. And even better than the size of this data set, I really appreciated their description of what a banana is, succinctly described as an elongated crescent-shaped yellow fruit with soft, sweet flesh, which both gives a pretty good description of what a banana is and speaks to its obvious deliciousness. So the creators of ImageNet also created a set of visual recognition challenges on their data set, and most notably the ImageNet classification task, which is really simple. It's produce a list of the different object categories that are present in images across a ground truth set of 1,000 different categories. And in this competition, they measured the accuracy of the models that were submitted in terms of the rate at which the model did not output the correct label in its top 5 predictions for a particular image. And the results of this ImageNet classification challenge are pretty astonishing. 2012 was the first time a CNN won the challenge, and this was the famous CNN called AlexNet. And since then, the neural networks have completely dominated this competition, and the error that the state of the art is able to achieve keeps decreasing and decreasing, surpassing human error in 2015 with the famous ResNet network, which had 152 convolutional layers in its design. But with improved accuracy, the number of layers in these networks has steadily been increasing. So take it as what you will. There's something to be said about building deeper and deeper networks to achieve higher and higher accuracies. So far, we've only talked about classification. But in truth, CNNs are extremely flexible architecture and have been shown to be really powerful for a number of different applications. And when we considered a CNN for classification, I showed this general pipeline schematic where we had two parts, the feature learning part and the classification part. And what makes a convolutional neural network is really this feature learning portion. And after that, we can really change this second part to suit the application that we desire. So for example, this portion is going to look different for different image classification domains. And we can also introduce new architectures for different types of tasks, such as object recognition, segmentation, and image captioning. So I'd like to consider three different applications of CNNs beyond image classification. The first is semantic segmentation, where the task is to assign each pixel in the image an object class to produce a segmentation of the image. Object detection, where we want to detect instances of specific objects in the image. And finally, image captioning, where the task is to generate a language description of the image that captures its semantic meaning. So first, let's talk about semantic segmentation with this architecture called fully convolutional networks, or FCNs. And here, the way it works is the network takes in an input of arbitrary size and produces an output of corresponding size where each pixel has been assigned an object class, which we can then visualize as a segmentation. And so as before, we have a series of convolutional layers arranged in this hierarchical fashion to create this learned hierarchy of features. But then we can supplement this, these downsampling operations with upsampling operations that increase the resolution of the output from those feature learning layers. And then you can combine the output from these upsampling layers with those from the downsampling layers to actually produce a segmentation. One application of this sort of architecture is to the real-time segmentation of driving scenes. So this was a result from a couple years ago where the authors were using this encoder-decoder-like structure where you have downsampling layers followed by upsampling layers to produce these segmentations. And last year, this was sort of the state-of-the-art performance that you could achieve with an architecture like this in doing semantic segmentation. And deep learning is moving extremely fast, and now the new state-of-the-art in semantic segmentation is what you see here. And it's actually the same authors as that previous result, but with an improved architecture, where now they're using one network trained to do 3 tasks simultaneously: semantic segmentation, shown here, depth estimation, and instance segmentation, which means identifying different instances of the same object type. And as you can see in this upper right corner, these segmentation results are pretty astonishing, and they've significantly improved in terms of their crispness compared to the previous result. Another way CNNs have been extended is for object detection, where here the task is to learn features that characterize particular regions of the input image, then classify those regions as belonging to particular object classes. And the pipeline for doing this is an architecture called RCNN, and it's pretty straightforward. So given an input image, this algorithm extracts a set of region proposals bottom up, computes features for these proposals using convolutional layers, and then classifies each region proposal. And there have been many, many different approaches to computing and estimating these region proposals. Step 2 in this pipeline, and this has resulted in a number of different extensions of this general principle. The final application that I'd like to consider is image captioning. And so suppose we're given this image of a cat riding a skateboard. In classification, our task could be to output the class label for this particular image, cat. And as we saw, this is done by feeding the image through a set of convolutional layers to extract features, and then a set of fully connected layers to generate a prediction. In image captioning, what we want to do is generate a sentence that describes the semantic content of the image. So if we take that same CNN network from before, and instead of fully connected layers at the end, we replace it with an RNN, what we can do is we can use a set of convolutional layers to extract visual features, encode them, input them into a recurrent neural network, which we learned about yesterday, and then generate a sentence that describes the semantic content that's present in that image. And the reason we can do this is that the output of these convolutional layers gives us a fixed length encoding that that we can use to initialize an RNN and train it on this captioning task. So these are three very concrete fundamental applications of CNNs. But to take it a step further in terms of sort of the depth and breadth of impact that these sort of architectures have had across a variety of fields, I'd like to first appreciate the fact that these advances would not have been possible without the curation and availability of large, well-annotated image data sets. And this is what has been fundamental to really rapidly accelerating the progress in the development of convolutional neural networks. And so some really famous examples of image data sets are shown here. MNIST, which you'll see in today's lab, ImageNet, which I already mentioned, and the Places data set, which is out of MIT, of different scenes and landscapes. And as I sort of alluded to, the impact of these sorts of approaches has been extremely far-reaching and deep. No pun may be intended. And one area that convolutional neural networks have made a really big impact is in face detection and recognition software. And this is, every time you pick up your phone, your phone is running these sorts of algorithms to pick up, your face and your friend's face. And this type of software is pretty much everywhere, from social media to security. And in today's lab, you'll have the chance to build a CNN-based architecture for facial detection. And you'll actually take this a step further by exploring how these models can be potentially biased based on the nature of the training data that they use. Another application area that has led to a lot of excitement is in autonomous vehicles and self-driving cars. So the man in this video was a guest lecturer that we had last year, and he was really fun and dynamic. And this is work from NVIDIA, where they have this pipeline where they take a single image from a camera on the car, feed it into a CNN that directly outputs a single number, which is a predicted steering wheel angle. And beyond self-driving cars, NVIDIA has a really large-scale research effort that's focused on computer vision. And on Friday, we'll hear from the leader of NVIDIA's entire computer vision team, and he'll talk about some of the latest and greatest research that they're doing there. Finally, there's been a pretty significant impact of these types of architectures in medicine and healthcare, where deep learning models are being applied to the analysis of a whole host of types of medical images. So this is a paper from Nature Medicine from just a few weeks ago, where it was a multi-institute team, and they presented a CNN that uses a pretty standard architecture to identify rare genetic conditions from analysis of just a picture of a child's face. And in their paper, they report that their model can actually outperform physicians when tested on a set of images that would be relevant to a clinical scenario. And one reason that work like this is really exciting is because it presents sort of another standardized approach to identifying and diagnosing, in this case, genetic disorders. And you can imagine that this could be combined with already existing clinical tests to improve classification or subtyping. All right, so to summarize what we've covered in today's lecture, we first considered sort of the origins of the computer vision problem and how we can represent images as arrays of brightness values, and what convolutions are and how they work. We then discussed the basic architecture of convolutional neural networks and kind of went in depth on how CNNs can be used for classification. And finally, we talked a bit about extensions and applications of the basic CNN architecture and why they have been so impactful over the past several years. So I'm happy to take questions at the end of the lecture portion. You feel free to come to the front to speak to Alexander or myself. So with that, I'm going to hand it off to him for the second lecture of today.